Hello students, welcome to the channel and welcome to the playlist. In this playlist we are discussing about the transmission line modeling and performance. So we are observing the different types of transmission line, we are observing their performances, and we are trying to derive the ABCD parameters and trying to do the modeling for the particular transmission line. So uh, in this playlist, up until now we have seen two videos in which we have discussed about short transmission lines, and we have also seen the nominal T representation for medium transmission lines. So if you haven't checked that out, these two things in previous videos, the link will be flashing on the I button on the top right hand side corner of your screen, so just click it and check it out. And by the way, this course or this playlist in particular, in which we are discussing about transmission line modeling, so it involves it requires you to understand the general concepts or general principles of power systems. So the general principles of power system is a prerequisite for this course, and if you don't know about it, no need to worry. We have a playlist for that we have created initially. So the link of the playlist is given in the description below. So if you want to know more about it, so just go there, click on the playlist, and watch the videos. You'll be all clear. Now, coming to the nominal pi representation, we have discussed that for medium transmission line, we have two methods or two ways which we can represent my medium transmission line. First one is nominal T method or nominal T representation, and another one is nominal pi representation or nominal pi method. About nominal T method, we have seen that in the previous videos. So today we are going to talk about nominal pi representation or nominal pi method to represent medium transmission line. So what happens in this method, our capacitance for each conductor is divided into two halves. See, this one C by 2, other one C by 2, right? And see, this one half is being lumped at sending end voltage, and the second one, the other one, is lumped at receiving end voltage, right? And it's very obvious that capacitance at sending end will have no effect on the line drop, right? So it's very obvious thing to know, but uh, the charging current must be added to the line current, right, in order to obtain the total sending end current. Because why? Because Kirchhoff said so. Remember KCL here. KCL is equals to IC2 plus IL, right? So quickly, let me give you a glimpse of the circuit of nominal pi representation. This Vs represents sending end voltage, Vr represents the receiving end voltage. Here IR represents the load current or receiving end current. My R given here is the resistance per phase. This XL represents the inductive reactance per phase. Uh, this C by 2 and C by 2 collectively calling, let's call it C. So it represents the capacitance per phase. Uh, Except that this is sending in current IS, and this is my line current IL, right? And here we have collected a load, and the current flowing through both capacitors is given as IC1 and IC2 respectively. So that is how your nominal pi representation looks like. You can see it is forming a pi here. See this straight line and this, it is forming a pi here. And again, what is happening, that my admittance or my impedance is not getting split. It is the whole here. We assume it, even though it is uniformly distributed over the line, but we assume it lumped over here. and what happens that my capacitance is divided into equal parts. Okay, and nominal T, it was reverse of it. My admittance or my impedance was divided in two equal parts, and my capacitance, shunt admittance or shunt capacitance was whole. But here we are dividing my shunt admittance or shunt capacitance per phase in two equal parts. Okay, so that was the representation. Now let's quickly go through the nominal pi representation phasor diagram. So if you have attended the previous lecture, it will be quite easy for you. So what we are doing, we are taking the VR as the reference point. So here you can see this VR is my reference point, and I am representing it with point OA. When we use points, it gets easier to represent it. It gets easier to indicate something. So we are using points this time, OA. Then the current IR will lag behind VR by angle phi r, which happened in the nominal T as well. Remember, this is my current IR and it is lagging from my VR at angle phi r. Now the charging current IC1 will lead VR by 90 degree. So IC1 is leading VR by 90 degree. Here you can see. And the line current IL will, what it will be? IL will be phasor sum of this IR and IC1, because see, what is IL? It is phasor, what is IL? It is phasor sum of this my IR and IC1. So same thing happens in phasor diagram as well. So my IL will be sum of my IC1 plus IR. The resultant will be IL, right? And after that, what we will do, we will see that the drop regarding related to my line current IL. So what is the drop related to line current? It will be IRL. So in phase of this IL, we will draw IRL here. So ILR, sorry, not IRL, ILR or RIL will be in same phase as IL, because it's the drop of that current, and it is resistive element, so there will be no phase difference. After when we draw the reactance element, then we will have difference ILXL, which will be 90 degree phase shifted. And when you what you do when you draw the next thing, which what it will be, it will be nothing but OC. See, to find VS, what do? We take resultant of this VR and the impedance, which will be the resultant of these two, right? The resultant of these two will look like something like this, right? It would look like this. And to find VS, what do? We sum that drop with VR. This plus this, and we will be left with VS, right? So that is how we plot VS, and uh, we represented it with OC here. Then the charging current C2, this charging current C2 will lead my VS by 90 degrees because of capacitor, and therefore the sending in current IS is a phasor sum of which two this time? It will be IL plus IC2, right? How do you know that? So come here, what is IS? So IS is IC2 plus ILC. IS is coming in, IC2 and IL are going out. So IS will be phasor sum of IC2 and IL this time. And the angle between the sending in voltage and sending in current, VS and IS, this VS and Where did my is go? This is will be phi s, right? It will be phi s. And based on that also we will define, or we will find the value of my power factor, sending in power factor, right? Phi s. Now as we already we discussed all these how all the derivation of the phasor diagram for nominal pi representation, it will be easy to understand what will be the formulas of this what will be formulas which will be associated my with my nominal pi representation, right? So what is vr? So vr is nothing but vr itself, because we took it as a reference. See, but you can always represent it in the form of in the complex form, even though it does not consist any complex element. See, it only consists real element, there is no complex element, but you can always represent it vr is equals to vr plus j into 0, because there is no complex, there is no imaginary value associated with it. Now come here and tell me what will be the value of ir here. What will be the value of this ir here, right? So can you tell me, it will be made up of two components, cosine and sine component. So we will just divide it. So IR will be IR cos phi r minus IR into j sin phi r. Right. We will take IR out and we will be left with IR is equals to IR cos phi r minus j into sin phi r. Because see, it is not it is neither parallel nor perpendicular to my reference axis, which means it will have both cosine and sine components, right? Now from here, can you tell me what will be the value of IC1? Rather than uh, deriving it from that, just let's just write down the current equation for the current flowing through a capacitor. So it will be j omega c by 2 into vr. uh, Again, why it was c by 2? Because see here, uh, my capacitance is getting divided into equal parts, so we will be considering c by 2 at a time. So we will have j omega c by 2 divided into vr. And mentioning omega, we will instead of omega we can write 2 pi f. So when we write it 2 pi f, 2 will get cancelled, and we will be left with j pi f c into vr, right? Now how can we represent the line current? So again, to find the line current, apply KCL at here, at this node. What will be left with, this IL is coming in, IC and IR are going out, which means IL is equals to IR plus IC1. So IL is equals to IR plus IC1. Now what will be my sending end voltage? We derived it from this phasor diagram, remember? So sending end voltage will be VR plus this drop, VR plus this drop. What is this drop? So this drop is addition, vector addition or a vector summation of these two, ILR plus ILXL. So let's mention it, VR plus this drop. What was that drop? IL into Z. So what was the value of Z? Z's value was R plus JXL. See, IL into R plus IL into XL. So we took IL common and we will be left with R plus JXL. So that will be my sending end voltage. Now to find the charging current at sending end, what will be the charging current at sending end? IC2. So the value of IC2 will be j omega c by 2, same as IC1, but this time the multiplication, instead of multiplying with VR, it will be multiplied with VS, because it is associated with sending end current, right? IC2, see here, come here and see here. See, this one is IC1 and IC1 is associated with receiving end. This is IC2, IC2 is associated with sending end. So in the formula of IC2, what we will get? We will get j omega c by 2 into Vs. And again, when you write 2 pi f instead of omega, 2 will 2 this 2 of the omega and 2 which was divided with capacitance will cancel out each other. and you will be left with j omega fc into Vs. Now same way is applying the KCL at this node. So here Is is coming in, IL is going out, IC is going out. So what we will get? We will get Is is equals to IC2 plus IL. Right, Is is equals to IC2 plus IL. So now that we have seen the formulas, phasor diagram and circuit diagram for it, let's try to derive this derive the ABCD parameters for my nominal pi representation. Okay, so let's come here and let's see. So our objective is to find the ABCD parameters or generalized circuit constants of nominal pi nominal pi represented medium transmission line. So what do we do here do in this case this time? So first let's see the figure. It is having same configuration as the first one, so that it will be very easy for us to understand, where we have not changed any analogy here. See, Vs is staying Vs, C by 2 is staying C by 2, C by 2 is staying C by 2, Vr is staying Vr, IL is staying IL, R and XL, IS, IR, everything is same as it was earlier, so that it will be very easy for you to grasp. So we kept it as it was, but instead of capacitance here we have take what did we do? We took shunt capacitance here, shunt admittance here, y by 2 and y by 2, right? And instead of mentioning R and XL we took Z whole, so that it will be easier to represent. Nothing, there is no other thing. It's just we took Z so that we can easily represent the whole impedance, right? So what will happen here? This line to neutral capacitance will be divided into two equal parts, right? Which is this one and this one. This one is concentrated on the load end, and this one is concentrated on sending end. Now I want to find the impedance. What will be the formula of impedance? It will be R plus jXL, right? There is no rocket science in that. It is very basic. What will be formula for my admittance, shunt admittance? So it will be j omega c. Okay, so we mentioned j omega c. What will be the value of my Is, which we just derived based on Kirchhoff's current law, which we applied on this node here, and we found out IL plus IC2, or we can also write IL plus what will be the value of IC2. See, what will be the value of my IC2? So value of my IC2, can't we say it will be equal to my Vs, this Vs into y by 2. What is y by 2? The admittance, shunt admittance of this side. So instead of IC2 we mentioned Vs into y by 2, or admittance divided by 2. Same ways we can also see here, applying Kirchhoff's current law at here as well. What we will get? See here, IL is going in, IR and IC are coming out, which means IL will be equal to IR plus IC1. So we just mentioned it here, IL is equals to IR plus IC1. We kept IR as it was, and instead of IC1, this time it is lumped on the receiving end, so can't we write it VR into y by 2? When it was lumped on the sending end, what did we wrote? We wrote Vs into y by 2. So this time we will write VR into y by 2. Okay, so that was the calculation part on current side. Now let's try to find the value on the voltage side. So can you tell me what will be the value of Vs, or what will be the formula for the Vs's derivation? So the formula for Vs's derivation will be this current, this voltage VR plus drop which is happening here. So it will be VR plus IL into Z, right? Now come to think of it, what is the value of IL, right? What is the value of IL? We have just derived it, we just found it. See, IR plus VR y by 2. So just substitute the value of IL here. So we get IR here, VR here, plus the value of IL. What was the value of IL? IR plus VR into y by 2, and we took this z, and we kept this z as it is. Now what do we do? Again, remember what was the how do we represented the line parameters, right? Let me show it to you again. Let me show it to you again. Where did it go? No, not this, not this. This one. See, how did we represent? Vs is equals to A into VR plus B into IR, and Is is equals to C into VR plus D into IR. So in the formula of Vs, what do? We try to develop a formula in which we have a term VR and term IR, and both are separated with addition sign, and there are some multiples with them, which are ABCD parameters. This was for voltages. For currents, same story again, this time for Is, and the formula will be C dot VR plus D dot IR, and again what are VR and IR? So they are receiving end voltage and receiving end current, and entity which is multiplied with VR will be C, and what will be divided with what will be multiplied with DIR with will be D. So let's try to mold our solution such that it looks something like this: Vs equals to A plus A dot VR B plus IR. Okay, so coming back here, when we do that, we will get what will be the value of Vs. Vs will be equal to IR, Vs is equals to VR, then 1 plus yz divided by 2 plus IR multiplied with z. So basically what did we do here? We just took all the values which included value VR. So here, see, this is the first one, this is the second one, and this is the third one. So what did we do? We took VR common, and we simplified it. So we got VR multiplied with VR multiplied with 1 plus yz divided by 2, and what was the other entity? It was IR. The other entity was IR. So how do you know? Come and see here. What was the other entity? See, it was IR. So we had VR and IR here. So coming at nominal pi representation, VR and IR. So here we had VR and IR. So another entity is IR here, and the something that is multiplied with it will be Z. Now again, coming to the value of Is, what was the formula of Is? Here you can see Is is equals to IL plus Vs y by 2. So now what we will do, we just found out the value of Vs, so we will just substitute no, we are not substituting value of Vs till now. We will just put the value of VL in here. So we have derived the value of VL. What was the value of VL? IR plus VR into y by 2. So we will just mention it IR plus VR y by 2, plus we will keep Vs as it is and y by 2 as it is. Okay. Then after, what we will do, we will put the value of vs we will put the value of vs from this formula. Okay, so this term will stay as it is, so ir plus vr into y by 2, so we will get this ir plus vr into y by 2 as it is. Then what did we get? This y by 2 comes out, it gets separate, it is coming out. Then this vs, what will be the value of vs? It will be this vr into 1 plus yz by 2 plus ir into z. So here you see vr plus 1 plus yz by 2 plus ir plus z. Now what we will do, we will try to simplify it. So see, from here to here when we go, we will keep ir as it is, vr y by 2 as it is. What do we do with this? We will simply multiply this with this. So what we will be left with? We will be left with vr into yz, vr into y by 2. Then we will have y square z by 4, and then we will have ir into yz divided by 2. So by doing that, we just simply took it and simplified it. So we got ir plus vr y by 2 plus vr y by 2, then vr y square into z by 4 plus y into ir z by 2. Now from this, let's again try to form try to form an equation which was similar to the equation which we saw earlier, which we saw here. So let's try to mold our equation in this way, in which vs will be equal to a into vr plus b into ir. So when we try to do that, what we will get? We will get ir into 1 plus yz divided by 2. So we took this ir here, and then this ir here, this ir, so separate. So here nothing will be left, so 1 plus we have yz by 2 here, so we put yz by 2. Same ways we will take all the terms which consist vr separate, so we will get vr separate. But there is something different here, that with vr we are also getting y as separate ways or common ways, and then we will simply add it. So what we will be left with? We will be left with 1 by 2. See here, we took vr out, we took y out, so what will be left will be 1 by 2 plus, again vr is out, y is out, so again 1 by 2 plus 1 by 2, right? So what is the value of 1 by 2 plus 1 by 2? It will be 1, so just mention it 1 plus, again vr common and 1 y common, but there is still other y, so we will be left with yz divided by 4. So here yz divided by 4 we got. So now we have formed it in the manner which was pretty much similar to this one. Let me get back to that again. This one again. So multiple of vr will be a in the equation of vs, multiple of ir will be b in the equation of vs. So coming back to that, what was the multiple of v? What was the multiple of vr, and what is the multiple of ir? So based on that, let's see it one more time. What was the multiple of ir? D. What was the multiple of vr? C. Right. So what we will get? We will get 1 plus yz by 2 as a, and 1 y into 1 plus yz by 4 as c, and a and d will be equal, so 1 plus yz by 2, and b will be plainly z. How? So come here and see, on the basis of value of is, where did it go? Wait a minute, guys. Where did it go? Okay, here. When we simplify it for is, right? When we simplified for is, we got this value, and based on is's value, we got this these two, 1 plus yz by 2, which was my a, sorry, which was my c, no, sorry, which was my d actually. 1 plus yz by 2 will be d because it is multiplied, it is multiple of ir. See, what is the multiple of ir? Come here in the equation of is. Let's check. Multiple of ir. So what is multiple of ir? It is d. Okay, so it is d. And multiple of vr will be c. So the value of c is y into 1 plus yz divided by 4. Now you are yet to find values of a and b. So to find the value of a and b, here we have formula of vs is equals to vr 1 plus yz by 2 plus ir into z. So in the formula of vs, multiple of vr is called a and multiple of ir is called b. Let's just verify it. Multiple of vr is a or not. Where did it go? See here, multiple of vr is a, right? Correct. And multiple of ir is b. So again, what we will do, we'll find the value of a and b, and value of a will be 1 plus yz by 2 and value of b will be z. And again, we will try to match our a and d here. We will verify the values of a and d will remain equal. And another way to verify that the parameters which we have derived are correct is to take subtraction of ad minus bc. So when we take this subtraction, basically a and d are equal, so it will be 1 plus yz by 2 whole square minus, we will take multiplication of b into d, so z into y, 1 plus yz divided by 4. So when you take this subtraction, and if you left with only 1, which so that will mean that your your ABCD parameters are derived correctly. If you do not get answer 1, that means your there is some error in your derivation. So that was nominal pi representation ABCD parameters, or you can also call them generalized circuit constants for nominal pi representation of medium transmission lines. Now let's quickly jump to the final part, which is nothing but the uh, voltage regulation and efficiency of my nominal pi network. So to calculate the voltage regulation of line, what do? We find the no load voltage, right? No load receiving end voltage by keeping sending end voltage constant. So we will do the same here, and we do so. We will the circuit will look like this. We will have Vs here, R and X are here. This is my capacitance, and we will find the voltage in voltage compared to this this capacitance. And we do so, the vr dash value will look like this: vs into 1 divided by minus y by 2 divided by my impedance, right? And voltage regulation again can be given by this formula: vr dash minus vr divided by vr into 100. Again here we have took the no load voltage by vr dash, and vr is my full load voltage, right? And what will be the efficiency? Efficiency will be power delivered at receiving end divided by power sent from the sending end. Again, we can divide the power delivered at sending end into two parts: power delivered at receiving end plus losses. So similarly, similar to my t representation, here we will be getting assume if total power we have, total delivered power is p. So it will be P divided by P plus 3 I square R. Why only I square R? Because my current is not getting separated here, right? What was happening with the with my nominal T representation, that my sending end and receiving end current uh, were I was getting different because of loss. But here we can take I square R, because why? Because my resistance or my impedance is not cut into half, it is whole. So we can write P divided by P plus 3 I square R. So that was the nominal pi representation of medium transmission line. I will keep this lecture till here, and in the next lecture I will be meeting you with high transmission lines operations. If you have any doubts, any queries related to this playlist or this subject or anything else, please feel free to mention them in the comment section below. If you have any suggestions, feedbacks, or anything related to videos, please feel free to drop them in the comment section as well. I will try to answer them as much as possible and as soon as possible. So I will be seeing you in the next lecture. Till then, take care everyone, and thank you very much for listening.